Yes, 5.3 was your method should give valid results. Oh dear, bad news for flat earthers. 5.3. A suitable method described for 1 point. The observations and measurements required to place in order. If, depending on you having a suitable method, 1 point. An indication of how results will be used to place the unknown metal in the reactivity series, 1 point. A control variable to give a valid result, 1 point. A control variable? Approaches that could be used. Measure the temperature change when it's added to copper sulfate. Same volume of solution, same concentration of solution, same mass of metal, same state of division of metal. Yeah, obviously you have to use the same sample presentation and the same amount of the same solution. Add the metal or salt solutions to salt solutions of the other metals. Okay. Or heat the metal with oxides of the other metals. Yeah, heating one metal with an oxide of another, like heating aluminium or magnesium with an oxide of iron, that can cause a reaction. You get magnesium oxide and iron. This is a reaction known as the Thermite reaction. Yeah, you can get it started, good luck stopping it. Measure temperature change on the salt solutions used, or observe whether a chemical change occurs. How do you know whether a chemical change occurs? You don't need to specify how you know, you just observe it. Place the metals in order of temperature change, or whether there is a reaction. Anyone from same volume of salt solutions, same concentration of salt solutions, same initial temperature of salt solutions, same mass or number of moles of metal or metal oxide, same mass or number of moles. You'd have to know that would have to be of the known metals. Same state of division. Present as slivers or powder or coiled ribbon or slab in each case. Approach 3. Add all of the metals to an acid separately. Measure temperature change, or the rate at which hydrogen comes fizzing out, or some such thing. Place the metals with that. Again, the same, yada yada. Approach 4. Set up electrochemical cells with the unknown metal as one electrode and each of the other metals as the other electrode. Measure the voltage. That's clever. But you'd have to put them the same distance apart in the same concentration of the same electrolyte at the same temperature. In the same places, in the same volume, in the same container, with the same lengths of wires and all kinds of same things. Right. And here we go. An exothermic reaction starts at one place, goes up, comes back down, stops in another place. Label reactants, products, label. Oh, this jump to here as activation energy, and this jump from here down, drop from here down to here as overall energy change of the reaction. One for the correct shape, one for labelling activation energy, one for labelling the energy change. Ignore arrowheads. Okay. Why would electrolysis not happen? Because solid zinc chloride does not conduct electricity? Okay. But yeah, I said because ions can't move in the solid, or only move in liquid or in solution. Yes. Each carbon atom forms 3 covalent bonds. 1 electron per carbon atom is delocalized. So these electrons carry charge through the graphite or move through the structure. This is why graphite conducts electricity, and that's pretty much what I said. Use measuring cylinders instead of test tubes, indeed. Because test tubes don't show volume. Indeed. The clue's in the name. Measuring cylinder. Ending 3 from, the volume of hydrogen collected is directly proportional to the time. Yes, it is. The rate is 0.5 cubic centimetres per minute. To 8 minutes, chlorine is collected at an increasing rate. After 8 minutes, the rate of collection of chlorine is the same as that of hydrogen, or is 0.45 cc per minute. Allow any value from 6 to 8 minutes. Okay. Initially, chlorine is collected at an increasing rate. say constant or steady rate. Okay, chlorine reacts with water dissolved in the solution. Yep. Volume 6.6 over 1,000 litres. Moles is that divided by 24, which is 2.75 times 10 to the negative 4, which I hope is what I said. Allow 2.8, just putting it to two sig figs. Alternative approach, convert the 24 cubic decimetre to 24,000 cubic centimetres. Yeah, then divide. It's the exact same calculations in a different sequence that ends at the same place. It's like asking whether the knight on a chessboard moves one place right and then two forwards, or two forwards and then one right. Potassium chloride and iodine. Seven one is down here somewhere. Thank you for this blank page, it really makes things better. Yada yada, yada 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 yada. Seven one. Name the product's form when chlorine solution reacts with potassium iodide solution. Potassium, chloride, and iodine. Phew. Yeah. Chlorine's outer electron shell, are closer to the nucleus, so chlorine nucleus has greater attraction for outer electrons, so chlorine gains an electron more easily. Yeah. Max of 2 marks if someone says chloride iodide instead of chlorine iodine. Ignore has fewer outer shells, but do allow has less shielding, which is caused by outer shells. Allow energy levels for shells throughout. That has to do with atomic emission spectra. Hydrogen chloride is made of small molecules, so it has weak intermolecular forces, and they require little energy to overcome. That was simple. Well, bonds broken is 4 times 412 plus, and bonds formed is 3 times 412 plus, rather than just ignoring the ones that are there on both sides. 290 kilojoules per mole. Oh, alternative method ignoring the 3 unchanged bonds, but you still get 290 kilojoules per mole. Cool. Chlorine is toxic. Allow carbon monoxide is toxic. Problems with sodium. Very exothermic, produces a corrosive solution of sodium hydroxide, produces hydrogen which is explosive/flammable. Yep. Argon is unreactive. Oxygen from air would react with the reagents or the product. Water vapour in the air would react with them as well. Yeah, the water vapour is a problem too. Metal chlorides are usually ionic, so metal chlorides are solid at room temperature. Okay, it's because it's ionic. Strong electrostatic forces between the ions. Yep. Titanium chloride must be covalent or have small molecules with weak force between the molecules, so they do not accept bonds. Sorry, with weak force between molecules do not accept bonds unless intermolecular bonds. But metal chlorides are usually ionic. Right, the weird thing is that titanium chloride is molecular, not ionic, and that's why it's a liquid. Okay. Sodium atoms lose electrons. This is oxidation. And there's the half equation, sodium to sodium ion plus electron. 8.7. Calculate the moles, you get the molecular mass, you get relative molecular mass, 190. And It's a missing bracket. 870 moles. It's doing it the way, but yeah. And the product is 211 moles. Sodium is in excess because 870 moles of sodium is more than the 844 moles needed, or because 211 moles of titanium tetrachloride is less than the 217.5 moles needed. Either way. Yeah, it's working out exactly how much will be needed, and say 20 kilograms is in excess or 40 kilograms is not enough. .8. What was question 8.8? 92.3% of 13.5 kilos is 12.5 kilos. Allow 12.4605 kilos. If you're going to give me that figure to 3 sig figs and that figure to 3 sig figs, you know, you probably want an answer to 3 sig figs, really. Question 9. It's a strong acid because it's completely ionized, completely dissociated. It's allowed, but apparently we say ionized now. It is dilute because there is a small amount of acid per unit volume. Ignore low concentration. Okay. 5.0. That's the pH. I was right. Choose titrations 3, 4 and 5 because it's the ones that are, you know, the ones that were within 0.1 cc's. The average is 22.13 or 13333 or, you know. Allow a correctly calculated average from an incorrect choice of titrations. You would only lose the 1 mark that was for choosing those 3 particular titrations correctly. Calculate the number of moles. Convert to concentration. We have that average. Divide by 1,000 because we're going from cc's to litres. Multiply by molarity, you get that number. Halve it to get the number of moles of acid that were neutralised. Divide by 25 and multiply by 1,000, also known as multiply by 40, to go from per 25 cc sample to per litre, and you get 0.0465 moles per litre. There's an alternative explanation given here, which is just the same thing but doubling in a different place rather than halving at that stage. Pipette measures a fixed volume accurately, a burette measures a variable volume. Can measure drop by drop, it can indeed. 0.03, 30 over 1,000, times the molarity, yeah, 0.126 grams. Yup, that was the calculation I did. So okay then, apparently I still remember how to do GCSE chemistry. Dread to think how I'd do on an A-level chemistry.